All right, so this is going to be our walkthrough for the homework assignment titled Semester 1 Review. This is just mostly a bunch of multiple choice questions. They cover some of the topics from this first semester. There'll be 3 or 4 more review assignments, so don't just use this one as your only review. This doesn't necessarily cover everything. They'll each cover, sort of different things. So our first question here is a limit as x approaches infinity of this rational function. So now we can evaluate this limit using a couple of different methods. We should know what the answer is right off the bat because it's a rational function where the degree of the numerator and the degree of the denominator are the same. So we can just divide the leading coefficients, right? So 5 divided by 4 here should just give us 5/4, which is our answer. But that wouldn't be good enough on a free response question. So we should know that one of the ways to do this is a limit as x approaches infinity of 5x squared over x squared minus 3x over x squared plus 1 over x squared all over 4x squared over x squared plus 2x over x squared plus 5 over x squared. But we're dividing everything by x squared because 2 is the highest degree. So this would give us a limit as x approaches infinity of 5x squared over x squared is 5, 3x over x squared is 3 over x, and 1 over x squared is just 1 over x squared. 4x squared over x squared is 4, and then 2 over x and 5 over x squared. And we would see that as x goes towards infinity, 3 over x is 3 over infinity, which is essentially 0. 1 over x squared is 1 over infinity, so 0. And we have a lot of 0 terms, and we're just left with a limit as x approaches infinity of 5/4, which is, of course, the limit of a constant is the constant. The other option would be to use L'Hopital's rule for this. We would note that both the limit as x approaches infinity of the numerator is infinity, and also the limit as x approaches infinity of the denominator is also infinity, which means that we can take the derivative of the top and the bottom, giving us a limit as x approaches infinity of 10x minus 3 over 8x plus 2, which we would then note that the limit as x approaches infinity of 10x minus 3 is infinity, and that the limit as x approaches infinity of 8x plus 2 is infinity. Therefore, we could use L'Hopital's rule again to get a limit as x approaches infinity of the derivative of 10x minus 3, which is 10, over the derivative of 8x plus 2, which is 8, which, well, 10 over 8 would be that limit because it's the limit of a constant, and that reduces to 5/4. So if this was the AP test, just look at the problem and put 5/4 because you know that's the horizontal asymptote. But on a free response question, you'd have to use one or the other of these methods. Either one would be fine. For our second question here, we've got a function f that we want to be continuous for all real numbers. And we know that f of x equals x squared minus 7x plus 12 over x minus 4 when x is not 4. So what this is essentially saying is we have a piecewise function that is f of x is equal to x squared minus 7x plus 7x, not xx, 7x plus 12 over x minus 4 if x is not 4, and it equals some number if x is 4. Well, we want to figure out what that number is. Well, we know that this function here that we're looking at is certainly going to have a hole, right, a removable discontinuity at x equals 4 because we can factor it into x minus 4 times x minus 3 over x minus 4 and see that the x minus 4s are going to cancel. And in fact, we should do this as a limit. We'll say the limit as x approaches 4 of f of x is this. The x minus 4s cancel. This gives us the limit as x approaches 4 of x minus 3, which is 4 minus 3, which is, of course, 1. Right? So in order for a function to be continuous, there's three criteria that have to be met. One is that the function has to exist. Well, our function exists. It's equal to a at x equals 4. Right, so first criteria is met. The second criteria is that the limit has to exist as we approach 4. Well, it does. It equals 1. And the third criteria is that the value of the function, which is a, must equal the value of the limit, which is 1. And therefore we get answer choice A, which is that a must be 1. All right, for this function, we will note that if we try to plug in 0 to this, we get 0 over 0. So if this was a free response question, we would note that the limit as x approaches 0 of sine x cosine x minus sine x is equal to 0. And also separately that the limit as x approaches 0 of x squared is equal to 0. Then we'd be allowed to use L'Hopital's rule and take the derivative of the top and the derivative of the bottom separately and write a new limit. So the derivative of the bottom is really easy, right? The derivative of x squared is just 2x. But the derivative of sine x cosine x minus sine x is a little bit longer. The sine x cosine x part is going to require the product rule. So that'll be sine x times the derivative of cosine x, which is negative sine x, plus the derivative of sine x, which is cosine x, times the cosine x. And then we'll subtract from that the derivative of sine x, which is cosine x. We can rewrite this if we want into a limit as x approaches 0 of, we could say cosine squared x minus sine squared x minus cosine x all over 2x. And what I would do here is I would rewrite this again using a double angle identity. You don't have to, but it's going to make your derivatives easier because we're going to have to do a second application of L'Hopital's rule. So cosine squared x minus sine squared x is your double angle for cosine. So this is a limit as x approaches 0 of cosine 2x minus cosine x over 2x. And then we would note that because the limit as x approaches 0 of cosine 2x minus cosine x is equal to 0, right, because that's the cosine of 0 minus the cosine of 0, that's going to be 0, and that the limit as x approaches 0 of 2x is also equal to 0, we can apply L'Hopital's rule again, giving us a limit as x approaches 0 of the derivative of cosine 2x, which is negative 2 sine 2x, using the chain rule. And then the derivative of the minus cosine should be a plus sine x. And it's all over 2. Well, this is actually really easy to evaluate, right? Because if we plug in 0 to this, the sine of 0 is 0. So our whole numerator is 0. And we now have 2 in the denominator. So this limit is equal to choice C, which is 0. For our next one here, we've got the limit as x approaches 0 of tangent cubed 2x over x cubed. So if we try to plug in 0 to this, we'll immediately see that the tangent of 0 is 0 and x cubed is 0. And we might be tempted to try L'Hopital's rule, which will work, but the derivative of tangent cubed 2x is going to end up giving us something that will have to be differentiated using the product rule. And we're going to have to obviously do this more than once, right, the L'Hopital's rule, because if I take the derivative of x cubed, I'm going to get 3x squared, which is still going to be 0. And if the numerator is still 0, then we'd have to do it again. And the derivative of the 3x squared, right, would then be 6x, which would still be 0. So we'd have to do it a third time. So we'd have to take 3 derivatives of that numerator, most likely, which just doesn't seem very pleasant. So we should just use one of our previous techniques for this problem, which is we can rewrite this as tangent 2x over x, all being cubed. And then if we can get tangent 2x over 2x inside this limit, we should be able to evaluate it really easily. Well, all we have to do is put in a 2 to the denominator and a 2 to the numerator. So when we do that, this 2 gets pulled out into the front. But as it does, we have to remember that it's actually 2 cubed. So we now have 2 cubed times a limit as x approaches 0 of tangent 2x over 2x all being cubed. Right? Because once I have the cubed on everything inside the limit, I can pull that cubed outside the limit. That was one of our rules for limits. Well, 2 cubed is 8, and the tangent of 2x over 2x as x approaches 0 is just 1. So we have 8 times 1 cubed, which is just 8. Choice D. Our next one here, we are trying to find a value k so that our function is continuous for all real numbers. And so we're given this piecewise defined function, right? 3kx minus 5 when x is greater than 2, and 4x minus 5k when x is less than or equal to 2. Well, for the function to be continuous at all real numbers, we just need to make the limit as we approach 2 from the left equal to the limit as we approach 2 from the right, because each individual piece of this would be continuous for all real numbers. So the only place we might have a discontinuity is where the two different parts match up. So we'll do the limit as x approaches 2 from the left of f of x, which should be the portion when we do x is less than or equal to 2. So that'll be 4 times x, or 4 times 2, minus 5k, which is 8 minus 5k. Then we need to do the limit as x approaches 2 from the right of f of x, which would be the portion when x is greater than 2. So that'll be 3k times x, which is 2, minus 5, or 6k minus 5. So really all we need is for 8 minus 5k to equal 6k minus 5. For whatever k value that's true, that is when this function is continuous for all real numbers. Well, we can add the 5 over to the left side, giving us 13, and the 5k to the right side, giving us 11k. So k is just going to be 13 over 11, which is choice B. For our next one here, we are asked to evaluate the derivative of this implicitly defined equation when x is equal to 2. Which means we're going to have to do implicit differentiation. So first off, the derivative of 3x squared is 6x. The minus 2xy will become minus 2x times the derivative of y, and then plus the derivative of negative 2x, which is minus 2, times y. So that's product rule for minus 2xy. And then plus 3 dy dx is equal to not 1, which is a common mistake, but is equal to 0, right? Because we have to remember we're taking the derivative of both sides. So we can now solve for dy dx. I'll just leave my 6x and my minus 2y on this side and bring the other terms to the other side. So I've got a 2x plus, well, actually it's a minus 3, right, when we subtract that 3 over, that are both being multiplied by dy dx. So dy dx is just equal to 6x minus 2y over 2x minus 3, which should be easy enough for us to evaluate, except that we are only given an x value, right? So we need to evaluate this when x is 2, but we don't know the y value. So we have to go back to our original equation and replace all the x's with 2 so that we can then solve for y. So 3 times 2 squared minus 2 times 2 times y plus 3y is equal to 1. Well, 3 times 2 squared would be 12. Then we have minus 4y plus 3y. Well, that's just going to be minus y is equal to 1. And I think we can see that that ought to give us y is equal to 11. So the point we're evaluating at is now the point 2, 11. So we'll just plug in 2 for x and 11 for y. We get 6 times 2 minus 2 times 11 over 2 times 2 minus 3. And that's 12 minus 22, which is negative 10, over 4 minus 3, which is 1. So negative 10 over 1 is just negative 10. All right, for this next one, we're just looking to take the derivative of this function. It's a product of two functions, x squared and root 3x plus 1. So we'll use the product rule. it should be the first function times the derivative of the second function, which is 1 over 2 root 3x plus 1, times the derivative of 3x plus 1. And then we'll add to that the derivative of x squared times the other function. And of course, all of these answer choices have a common denominator for them. So what we need to do is get that common denominator, which means we need to multiply this second piece by 2 root 3x plus 1 in the denominator, as well as 2 and root 3x plus 1 in the numerator. Now we should be able to simplify this down, giving us a 3x squared in the first part, and then plus 4x, that's the 2x and the 2, times root 3x plus 1 times root 3x plus 1. Well, root 3x plus 1 times root 3x plus 1 is just 3x plus 1. And then in our denominator, we have 2 root 3x plus 1. A little bit more simplification gives us 3x squared plus 12x squared, which is 15x squared. And then plus 4x times 1 is 4x over 2 root 3x plus 1. So it looks like that is answer choice D. All right, our next one here is just asking us for the second derivative of this at x equals 3. So we need a first derivative, f prime of x, which will be 4x cubed minus 4x plus 5 using the power rule. Then we'll need a second derivative of this, which is going to be 12x squared minus 4. And we want f double prime of 3, so that'll be 12 times 3 squared minus 4, right? Well, 12 times 9 is 108, and 108 minus 4 is 104. Choice E. Our next one here is again just asking for a derivative. This function is a function that is u to the fifth, where u is equal to x squared minus 2x plus 1. And so it's just the power rule, but with the chain rule as part of it. So we want 5u to the fourth, or 5, times x squared minus 2x plus 1 to the power of 4. And then we want to multiply that by the derivative of x squared minus 2x plus 1, which is 2x minus 2. Now the problem here is we look at our answer choices, and none of our answer choices seem to look like this. So now what we need to do is we have to think about if there's any factoring we can do. Well, x squared minus 2x plus 1, that's a perfect square trinomial. That's just x minus 1 squared. So I've got x minus 1 squared to the fourth. And then 2x minus 2 is just 2 times x minus 1. So really what I've got here is a 5 times a 2, which is 10, times x minus 1 squared to the fourth, which would be x minus 1 to the eighth. But then I have another x minus 1, which means it'll actually be to the power of 9. So we can simplify this into 10 times x minus 1 to the 9th power. All right, here's another one where we're just taking a derivative and then evaluating it at a number. So since it's natural log of x over e to the x, we just need to use the quotient rule because that's a quotient of two functions. So f prime of x is going to be the denominator times the derivative of the numerator, right, minus the numerator times the derivative of the denominator. The derivative of e to the x is just e to the x, all over the denominator squared. And we want to evaluate this when x is equal to 1. Well, first of all, we know that the natural log of 1, right, is just 0. So this whole second term is going to go away. Then we have e to the first over 1, right, for this term. And then that's divided by e to the first to the second power. So really what we've got is e over e squared, which should simplify down to 1 over e. All right, our next one here is asking how many critical values f of x equals the sine of 2x has on the half open interval from 0 to 2 pi. So critical values are places where your derivative is equal to 0 or where your derivative is undefined. So we have to take a derivative, f prime of x. We'll use the chain rule on that, right? So it's the derivative of sine of u, which is cosine of u, where u is 2x. And then we have to multiply it by the derivative of 2x. So 2 cosine 2x. Now we know that's never going to be undefined, but it's definitely equal to 0 sometimes. And so we then think that 2 right here doesn't really matter, right? We don't really care about that. Really, we just care about when does cosine of 2x equal 0. Well, the cosine function equals 0 at pi over 2. So when the angle, which is 2x, is pi over 2. And also when the angle is 3 pi over 2. So these are 3 pi over 2. Or we could, we don't even really need to, well, we'll do it this way. But of course, because the cosine function repeats every 2 pi, we need to add a 2 pi in to each of these, right, where n is any integer. Now, the other option is we could recognize that it's equal to 0, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on, which is really pi over 2 plus every pi n. But since we started it this way, we'll just continue with this. If we divide everything by 2, we get x is equal to pi over 4 plus pi n, and x is equal to 3 pi over 4 plus pi n. So all we have to do is put in values for n, right? N equals 0, n equals 1, n equals 2, 3, 4, just integer values until we no longer are getting things on our interval from 0 to 2 pi. So if n is 0, we get x is equal to pi over 4 plus 0, as well as we get x is equal to 3 pi over 4 plus 0. Right? So those two values already. When n is equal to 1, we'll end up getting x is equal to pi over 4 plus pi times 1. That's 5 pi over 4. That's still on our interval. And then x is equal to 3 pi over 4 plus pi, which is 7 pi over 4. And that is also still on our interval. When n equals 2, though, we end up with pi over 4 plus 2 pi n. That'd be 9 pi over 4. Well, right there we know that's outside of our interval. So we have 4 critical values. All right, for our next one here, we want to know about the function natural log of 3x squared minus 6x at x equals 3. We want to know if it's increasing or decreasing. And we also want to know if it's concave up or concave down. And then one option is that f just doesn't exist. So we should really check and just make sure that the function exists at x equals 3. Right? We end up getting the natural log of 3 times 3 squared, which would be 27, minus 6 times 3, which is 18. Right? So we get the natural log of 9. Right? So the function does exist. We can ignore this. Now we need to determine if it's increasing or decreasing, and whether it's concave up or concave down. So first we'll determine if it's increasing or decreasing by evaluating the derivative at 3. So f prime of x should be, well, the derivative of the natural log of u is 1 over u times the derivative of u, which is 6x minus 6. Now, I think it'd be maybe nice to just simplify this down a little bit, just to make our arithmetic a little easier. If we divide everything by 3, we get 2x minus 2 over x squared minus 2x. Right? And so if we evaluate that, then when x is 3, we end up getting 2 times 3, which is 6, minus 2, over 3 squared, which is 9, minus 6. Well, the top is positive, and the bottom is also positive. Right? We get 4/3 here. That's greater than 0, which means that f is increasing, which means we can eliminate choices C and D. Then we'll need to take a second derivative to determine if it's concave up or concave down. So f double prime of x Well, that'll be the quotient rule with our derivative. So that'll be x squared minus 2x times the derivative of 2x minus 2, which is 2, minus the numerator, 2x minus 2, times the derivative of x squared minus 2x, which is 2x minus 2. All over x squared minus 2x squared. And I don't really need to worry about that denominator, because I know that if I evaluate x squared minus 2x and then squared, I'm going to get a positive number as long as x squared minus 2x doesn't equal 0, which if we plug 3 into that, it's 9 minus 3. Sorry, 9 minus 6, which is 3. So that denominator is going to be positive. So we end up with f double prime of 3 being 3 squared, right, which is 9, minus 2 times 3, which is 6, times 2, minus the 2x minus 2 times the 2x minus 2. Well, 2 times 3 is 6, 6 minus 2 is 4, right? So we've got 4 times 4, and as we just said in the denominator, that's 3 squared. So it looks like we've got 3 times 2, which is 6, minus 16 over 9. Well, 6 minus 16 is clearly negative. I don't need to worry about doing the rest of this. It tells me that it's concave down. I don't need to simplify any further. All I care about is the sign, which means that the answer is choice B. F is increasing, and it is concave down. All right, for our next one here, we want to figure out when the function is concave up, which means we need a second derivative. So f prime of x is equal to the power rule derivative of this. So 1/4 x to the 4th will just become x cubed, right? Because 4 times 1/4 is 1. And 9/2 x squared will become minus 9x. Now, I don't really care about what happens with the first derivative because we're talking about concave up. So we want f double prime of x, which is 3x squared minus 9. So that's never undefined, but it does equal 0 when x squared equals 3. Right? If you add 9 to both sides and then divide by 3, you get x squared equals 3. Or x is equal to positive or negative root 3. So we'll make a sign chart for our second derivative with negative root 3 and positive root 3. And we'll test to see when that second derivative's values are positive, because that's what makes a function concave up. So if I plug in something between those, like 0, I get 0 minus 9, which is negative, which means that my function is concave down between negative root 3 and root 3. If I plug in something more than 3, like a billion, 3 times a billion squared minus 9 is definitely positive. And the same will happen if I plug in something like negative a billion, right? Because when we square a negative, we get a positive, a really big positive if we're squaring negative a billion. And when we multiply that by 3 and subtract 9, it's still positive. So our function is concave up on the interval from negative infinity to negative root 3, and then from root 3 to infinity, which is answer choice E. For number 14, we're looking for when this function has a local maximum. So in order to figure that out, we need to figure out when our derivative is equal to 0 or undefined. So we'll use the product rule. F prime of x is equal to the first function times the derivative of the second function, which we'll use the power rule for. And then the derivative of the first function, which is still just e to the x, times the second function. Well, then all we have to do is factor out the e to the x and combine like terms. We'll have an x squared. We have a plus 2x and a minus 2x, which will cancel, and a minus 2 and a plus 3, which will be plus 1. So we have e to the x times x squared plus 1, which we know is never undefined. And we then check to see when it's equal to 0. Well, e to the x is never 0 because it's always positive, right? If you take a positive number and raise it to any power, you get a positive. And x squared plus 1, well, x squared is always either 0 or positive. And if I add 1 to it, that's always going to be positive 2, which means this does not have any critical values. And if a function does not have any critical values, it can't have any local maxima or minima, right? Unless it has an endpoint somewhere. And this function is defined for all real numbers and therefore it will not have a local max or, in fact, a local minimum. All right, for our next one here, we're looking for f prime of root pi over 4, and we're given f of x is sine cubed of x squared. So we need to take the derivative of that using the chain rule, and then evaluate it at root pi over 4. So sine cubed of x squared is like u cubed, where u is the sine of x squared. So this is 3u squared times the derivative of the sine of x squared, which is like the sine of v, where v is x squared. So its derivative is the cosine of v times the derivative of v, which is 2x. So effectively, we've got 6x, and then u squared, so that'll be sine squared of x squared, and then cosine of v, which is cosine of x squared. So that's our derivative. And now we want to evaluate it at root pi over 4. So we have 6 times the square root of pi over 4 times the sine of root pi over 4 squared, and then we square that. So this is sine squared of pi over 4 and cosine of pi over 4. Well, we know that the sine of pi over 4 and the cosine of pi over 4 are both root 2 over 2. So what we've got here then is a 6, and then we've got our root pi over 4 still, and then we've got root 2 over 2, which we're squaring, and then we've got another root 2 over 2. And so as we simplify this down, the 6 is kind of going to stay up there for now. We're going to have a 6, but we're still going to have a root pi, and then root 2 squared is just 2, so we're going to have a 2 from that, and then a root 2. And then in the denominator, the root 4 here is going to be a 2 in our denominator. And then the 2 squared will be a 4 in our denominator, and then we have another 2. So some of these 2's will cancel. We cancel a couple of the 2's out, and 6 over 2 should just be 3. So in the end, we've got 3, and we've got a square root of 2 and a square root of pi, so root 2 pi. And since we simplified the 6 with the 2, that 2 goes away, and we're just left with a 4 in the denominator, so we get 3 root 2 pi over 4. All right, for our next one here, we got a limit as x approaches -2 of 2x squared plus 7x plus 6 over x plus 2. So we have a couple of options here. One option is, well, after we plug it in, because once we plug this in to begin with, we see that it's 2 times -2 squared, which would be 4, and then plus 7 times -2 plus 6. Right, we end up with 0 in the numerator and 0 in the denominator. So one option is to just factor. I'd say this is the limit as x approaches -2 of the x plus 2 will remain in the denominator. And we can be pretty well clued in that the top has to have a factor of x plus 2 so that I can cancel them out, which leaves us with a 2x plus 3. And we always want to check 3x and 4x does make the 7x there. So we could then rewrite this as just a limit as x approaches -2 of 2x plus 3, which would be -4 plus 3, which would, of course, be -1. Now, the other option is to say, well, the limit as x approached -2 of the numerator was 0, and the limit as x approached -2 of the denominator was also 0. Therefore, we can use L'Hopital's rule and take the derivative of the top and the derivative of the bottom, giving us a limit as x approaches -2 of 4x plus 7 over 1. And if we evaluate that, we get -8 plus 7, which is also -1, right? We get the same answer. So either way is perfectly acceptable. For our next one here, we want to use the mean value theorem to find all values of c on the closed interval 0 to 2 that satisfy f prime of c is equal to f of b minus f of a over b minus a, right? This is just the mean value theorem. So the first thing we always need to do when we use the mean value theorem is to see if the function is continuous on that interval. And right off the bat, we look and say, oh, this function has a discontinuity. In fact, it happens to be an infinite discontinuity. We'll write that at x equals positive 1. Well, positive 1 is on the interval 0 to 2, which means that the mean value theorem does not apply because f is not continuous on that interval. If it was continuous, then we'd need to check if it was differentiable. And if it was, then we would use the mean value theorem. All right, for our next one here, we've got a limit as x approaches infinity of 3x minus 2 over root x squared minus 1. This is one of the functions that kind of puts us in an infinite loop if we try to use L'Hopital's rule on it. It is infinity over infinity, but as we talked about in class, L'Hopital's rule just kind of doesn't work for it. Luckily, we had another method way back from our limits unit, which was to rewrite it by dividing by an x squared within the square root of that denominator, which means we're going to divide the 3x minus 2 also by a square root of x squared. But before we move to the next step here with the new limit as x approaches negative infinity, we need to think a little bit about what square root of x squared is. The square root of x squared is the same thing as the absolute value of x. Those are identical things. But dividing by absolute value of x is not so great either. So we need to think about that. The absolute value of x is equal to x if x is greater than or equal to 0. But it's equal to the opposite of x if x is less than 0, right? If we have a positive number or 0 that we put into the absolute value just returns the same initial value. But if we put in a negative number, like negative 2, the absolute value returns us the opposite of that negative number, the positive. Right? So the absolute value of x is equal to the opposite of x if x is less than 0. Well, in this problem, x is approaching negative infinity, which means that x is less than 0, which means that the square root of x squared that we have up here, this square root of x squared, is really absolute value of x, and that absolute value of x, since x is approaching negative infinity, is really the opposite of x. So we end up with 3x minus 2 over the opposite of x, over the square root of x squared over x squared is 1 minus 1 over x squared. And so we just get a limit as x approaches negative infinity of 3x over the opposite of x is negative 3, and negative 2 over negative x is plus 2 over x, all over root 1 minus 1 over x squared. As I put in negative infinity to this, the 2 over x is just like 0, and the 1 over x squared is like 0. So we have negative 3 over the square root of 1, which is negative 3. All right, for our next one here, we've got a spherical balloon. It's got a volume of 4/3 pi r cubed, and it's slowly deflating at a rate of 10 cubic inches per minute. We want to know at what rate is the radius changing when r is 5. Well, this sounds a lot like a related rates question. We're given one rate and we're asked for a different one. So first, let's sort of figure out what different rates we have and what we're looking for. It's deflating at 10 cubic inches per minute, which tells us that dv dt, right? We're including that it's a change in the velocity with respect to time because of the cubic inches per minute. And since it is deflating, that means that the volume is getting smaller. And anytime a quantity is getting smaller, then we have to have a negative rate of change. So it'll be negative 10 inches cubed per minute. We are looking for the rate of change of the radius. And then we are interested in it when the radius is 5 inches. So all we have to do is take our volume equation here and take the derivative of both sides of it with respect to time, which will give us dv dt is equal to 4 pi r squared dr dt. Right? So it's implicit differentiation with respect to t. Well, dv dt is negative 10. 4 pi is just 4 pi. R was 5, so that'll be 5 squared times dr dt. So we have negative 10 equals 5 squared is 25 times 4 is 100, so equals 100 pi dr dt, or dr dt should be equal to negative 1 over 10 pi inches per minute. So negative 1 over 10 pi inches per minute, choice A. Okay, back to another easy one here. The function we have is the inverse tangent of x squared. We just want f prime of 2. So we just take the derivative of inverse tangent of x squared using the chain rule. Right, so inverse tangent u is 1 over 1 plus u squared. And then we multiply by the derivative of u. So this is f prime of x, or 2x over 1 plus x to the 4th. We just want to know what this is when x is equal to 2. So we'll evaluate this at x equals 2. The numerator is 4, and the denominator is 1 plus 2 to the 4th, which is 16. So we get 4 over 17. Choice D. For the next one here, number 21, we're looking at the tangent line to this implicitly defined curve at the point 1, 1. So in order to write the equation of a tangent line, we need a point and a slope. We're already given the point, so we just need to find the slope by implicit differentiation. So the derivative of x to the 4th is 4x cubed. For the derivative of 3xy squared, we'll need to use the product rule, so that'll be 3x times the derivative of y squared, which is 2y dy dx, plus the derivative of 3x, which is 3 times y squared. And then, of course, we have to add to that the derivative of 5y cubed, which is 15y squared dy dx. And it's equal to the derivative of 9, which is 0. We'll solve for dy dx. So I'll leave my 4x cubed and my 3y squared on the left side. And I'll take all the other terms to the right-hand side. They both have a dy dx attached to them. So I know I'll be able to factor that out. And it'll be a negative 15y squared and a negative 6xy when I multiply the 3x with the 2y. So dy dx is equal to 4x cubed plus 3y squared over negative 15x squared minus 6xy. And we're asked to evaluate this when x is 1 and y is 1. So all the x's and y's just become 1s. We have 4 plus 3 over negative 15 minus 6. 4 plus 3 is 7. Negative 15 minus 6 is negative 21. So we get negative 1/3 as our slope. So our final answer should be y minus 1, because our y value is 1, equals negative 1/3 times x minus 1, because our x value was 1. So y minus 1 equals negative 1/3 times x minus 1. Looks like choice B. All right, our next one here, we're looking for f prime of 0 when f of x is root x squared plus 5x plus 25 times x squared plus x plus 1 cubed, which means we just need to take the derivative of this. We'll take the derivative of it using the product rule. So it'll be, first of all, the first function, root x squared plus 5x plus 25, times the derivative of x squared plus x plus 1 cubed. Well, that's u cubed. So that'll be 3 times u squared times the derivative of u, which is 2x plus 1. Then we'll add to that the derivative of the root x squared plus 5x plus 25, which is 1 over 2 root x squared plus 5x plus 25, times the derivative of x squared plus 5x plus 25, which is 2x plus 5, and then times the second function, which is x squared plus x plus 1 cubed. So that's our derivative. And we want to evaluate that when x is 0. Well, if x is 0, x squared and 5x are both 0. So this is just the square root of 25 times 3. X squared and x will both just be 0. So that's just 1 squared. 2x will just be 0. So that's just 1. And then we'll have 2x plus 5, which will just be 5. And x squared plus x plus 1, which will be 1 cubed, over 2 times the square root of 25. And we'll just evaluate that all out. So like square root of 25 is 5, times 3 is 15, times all those 1s is still 15. So we have 15 plus, we've got 5 in the numerator and 2 times 5 in the denominator. So 15 plus 5 tenths. Well, that's 15 plus 1/2, which would be 30 halves, plus a half, which would be 31 over 2. Choice C. Number 23 here is somehow one of the most missed questions. The derivative of 4 to the x. All you have to do is know the rule, right? The rule says the derivative of a to the x is a to the x times the natural log of a. That's the derivative. If you just know the rule, it should be pretty straightforward. You look at all your options. That's not true. That's not what it is. That's different. That's different. So it's just none of these. Number 24 here is an inverse function question. So it says f of g, or f and g are inverses. 3, 1 is on f. So f contains the point 3, 1, which we know means g contains the point 1, 3. Well, we want g prime of 1. The inverse rule just says that g prime of 1 should equal, if f and g are inverses, 1 over f prime of its x value at that related point. Well, we're given f prime of 3, it's 7, so g prime of 1 ought to be 1 over 7. Choice B. And our next one here wants us to find all increasing, decreasing intervals, local maxes and mins, intervals of concave up and concave down, and points of inflection for this function x minus 3 times the cube root of x. So we're kind of done with the multiple choice here for our non-calculator problems. This one's going to be a little bit more time consuming, but to find increasing and decreasing in the maxes and mins, we need to take a first derivative. So f prime of x is 1 minus, and then 3 cube roots of x is 3x to the 1/3. So the derivative of 3x to the 1/3 should just be x to the negative 2/3. Or in other words, we've got 1 minus 1 over x to the positive 2/3. We can, of course, get a common denominator there if we want to, right? Multiply this by x to the 2/3 and this by x to the 2/3, giving us x to the 2/3 minus 1 over x to the 2/3. To determine when it has a max or a min, when it's increasing and decreasing, we need to know two things. One, we need to know when is it undefined. So f prime is undefined if that denominator is 0, which would be when x is 0. So there's one critical value. And it's equal to 0 if x to the 2/3 minus 1 is equal to 0. Well, that would tell me that x to the 2/3 is equal to 1, right? Or, we can cube both sides of this to give us x squared is equal to 1. And then when we square root, we will get x is plus or minus 1. So we've got 3 critical values. We've got 0, we've got 1, and we've got negative 1. So we'll put all of those on a sign chart, and we'll test the values on each of the intervals. So something more than 1, like a billion, if I take a billion and raise it to the 2/3 power and subtract 1, it's still positive. And if I do 1 billion to the 2/3 power, in the denominator, that's just positive. In fact, anything to the 2/3 power other than 0 is going to be positive, right? We cube root it, but then we square it. So whether it's a negative or a positive, that's always going to be positive. So I can kind of ignore that as I go through with my sign chart. Now, if I do something between 0 and 1, like let's say 1/8, because that's kind of easy to deal with. 1/8 cube rooted, and that numerator is 1/2. And when I square 1/2, I get 1/4. But 1/4 minus 1 is negative. So that interval, the function is decreasing. And the same is going to happen if I pick something like negative 1/8, which is between negative 1 and 0. The cube root of negative 1/8 is negative 1/2. And when I square that, I get positive 1/4 minus 1, which is still negative. But if I put in negative 1 billion, the cube root of that is still negative, but when I square it, it's a really big positive number. And when I subtract 1, I'll still get a positive. So we can see that what our function does here is our function increases, then our function decreases, then our function increases again. So if we're writing out the intervals, we can say it's increasing on negative infinity to negative 1, and then again from 1 to infinity. And we can say that it is decreasing on the interval from negative 1 to 1. We also need to figure out what the actual values of our function are at 1 and negative 1. So f of negative 1 and f of 1, well, if we plug those in, we get negative 1 minus 3 times the cube root of negative 1, which is negative 1. So we get negative 1 plus 3, which is 2. And to find f of 1, we get 1 minus 3 times the cube root of 1, so we get negative 2. So we have a local max of 2 at x equals negative 1, and we have a local min of negative 2 at x equals positive 1. So that's the first half of the question. Second half of the question is going to get us to find the second derivative. So our first derivative was 1 minus x to the negative 2/3. So f prime of x was 1 minus x to the negative 2/3. From that form, it should be really easy to find our second derivative. Our second derivative, the 1 will go away. A negative 1 times a negative 2/3 will be a positive 2/3 out in front. X to the negative 5/3, or 2 over 3x to the 5/3. Now, this is equal to 0 never, right? Because the numerator is 2. So the fraction can't equal 0 if its numerator is 2. But f double prime is undefined if x is equal to 0. So we need to make a sign chart that only includes 0 for our second derivative. If we put a positive number into this, any positive to the 5/3 power is positive. And if I multiply that by 3 and do 2 divided by that, I'm still going to get a positive. But any negative number to the 5/3 power is going to stay negative, right? You'll cube root it, it'll stay negative. You'll raise it to the 5th power, it'll stay negative. So we end up with a negative times 3 and then 2 divided by that, which is a negative. So we can see that we are concave up on the interval from 0 to infinity, and we are concave down on the interval from negative infinity to 0. And we have a point of inflection at f of 0. Well, our original function was x minus 3 times the cube root of x. Well, x is 0, so that's 0. And then we have 3 times the cube root of 0, which is 0. So our point of inflection is the point 0, 0. All right, our next one here, we've got a window that is being built in the shape of a rectangle with a semicircle sitting on top of it, where the diameter of that semicircle is the same as the width of the rectangle. So here's the rectangle, and here is the semicircle. Make that a little bit bigger. The semicircle that is sitting on top of it. Right? And so what this says here is that we've got 12 feet of material to make the frame, and we want to know how wide the window should be to have the maximum window area. Right? So if we call this our width, and I guess we can call this the length if we want, or we can give it whatever variable we want. We'll just give it L. That means that the width of the rectangle is the same as the diameter. Well, the diameter of a circle, right, is just equal to twice the radius. So our width is 2 times the radius. And this is going to be kind of useful for us because we're trying to maximize the area. Well, the area should be 1/2 pi r squared. 1/2 pi r squared plus the length times the width, or 2r times L. Well, we also know that we have 12 feet of material to make the frame, which is essentially the perimeter of this thing minus this little piece here that goes between the rectangle and the semicircle, right? So that's not part of the frame of our window. So our perimeter, which is 12, should equal, well, we're going to have a W, which is 2r. We're going to have another W, which is another 2r. I'm sorry, we're not using that. We just said we weren't using that. So we have 2r. And then we have our L with another L, so 2r plus 2L. And then we have whatever the length of that semicircle is. Well, the length of the semicircle, right, should just be half of the circumference of that circle. And the circumference is 2 pi r. So this piece that's half of it should just be pi r. So we've got that 12 should equal 2r plus 2L plus pi r. Or in other words, if we solve that for L, L will be 12 minus 2r minus pi r, right? If we subtract the 2r and the pi r over, we have a 2L left, so then we just need to divide all that by 2. Which means we can rewrite our area equation into what will be our maybe not our final area equation, but a nice new one here. 1/2 pi r squared plus 2r times L, which is 12 minus 2r minus pi r all over 2. And now we can simplify that down a little bit, right? We'll have the area is equal to 1/2 pi r squared plus, the 2 here can cancel with the 2 here. So we'll be left with 12r minus 4, minus 2r squared minus pi r squared as our area function here. And then I can then combine together the 1/2 pi r squared with the negative pi r squared to get a final area equation, which will be negative 1/2 pi r squared plus 12r minus 2r squared. So there's our area equation, negative 1/2 pi r squared plus 12r minus the 2r squared. And then we need to figure out when that's at a maximum. So we'll put this on a new page so we can take its derivative. I'll rewrite that. It was the area is negative 1/2 pi r squared plus 12r minus 2r squared. So a prime should be, well, if we do negative 1/2 pi r squared and multiply by the 2 there, we get negative pi r using the power rule plus 12 minus 4r. So we just want to set this equal to 0 because it's clearly never going to be undefined. To set that equal to 0, seems like the best thing to do would be to add the 4r and the pi r to the other side. So we have 4r plus pi r over here. And to solve for r, we just need to factor out the r. And we have 12 equals r times 4 plus pi, where r is equal to 12 over 4 plus pi. Okay? So we do need to show that this is what yields us a maximum. So we have two options. One is to make a sign chart, but because this is kind of an annoying number to deal with, what I'm going to do is I'm just going to take a second derivative. Since this is a place where my derivative was 0, the second derivative test should work. And it's really easy to take the derivative of a prime. Right? The derivative of negative pi r is negative pi. The derivative of 12 is 0, and the derivative of negative 4r is negative 4. Well, negative pi minus 4 is clearly less than 0, which tells us that the function is concave down, right? And concave down gives us a maximum. So we clearly have a max when the radius is 12 over 4 plus pi. So then be careful, always go back to the original equation. What does it say? It says, how wide should the window be for that maximum area? Well, that'd be the width. Well, remember that the width is equal to 2 times r. So our width is 2r, which would just be 24 over 4 plus pi. And make sure you always include the units. And I don't remember what the units were. It looks like the units were all in terms of feet. So it's 24 over 4 plus pi feet. All right, for our next one here, we're looking again at an inverse rule problem. So if g is the inverse of f, and f is 2x plus ln x, we want to write the equation of the line tangent to g at x equals 2. So first of all, that tells us that g has a point 2 comma something, which means that f, its inverse, must have a point something comma 2, right? Because that's how inverse functions work, right? We flip the x and the y values because they're reflections of each other over the line y equals x. So it makes sense that the x and the y value should flip. So then we need to just set 2x plus ln x equal to 2, right? Because that's what the y value for f was, is 2. Well, this looks like it's going to be exceptionally difficult to solve and find a value for, except that we know that the only two numbers that are like kind of easy numbers to deal with that get rid of a natural log and turn it into just like a whole number are the natural log of e, which is 1, and the natural log of 1, which is 0. And natural log of e being 1 doesn't really help us because then I would have 2e plus 1, which is definitely not 2. But if I plug in x equals 1 to this, I get 2 times 1 plus the natural log of 1. Well, that's 2 times 1, which is 2, plus 0, which is clearly 2. Which means that the x value on f is 1, and the g values, or the y value on g is also 1. So now we've found this point that they have that's related, which tells us that if we want g prime of 2, and the reason we want g prime of 2 is because we're trying to write the tangent line to g at 2. Right? So we want g prime of 2. G prime of 2 should be 1 over f prime of 1 according to this inverse rule. So, well, f prime of 1 we'll need to find. So we need to find f prime of x first. Well, f prime of x will be 2 plus 1 over x, right? Because the derivative of 2x is 2, and the derivative of ln x is 1 over x. So now we want f prime of 1, which will be 2 plus 1 over 1, or 3. So f prime of 1 is equal to 3, which means that g prime of 2 is equal to 1 over 3. Well, now we've got the point for g and the slope. So we'll just write our equation in point-slope form. Y minus 1 equals 1/3 times x minus 2. All right, so the rest of these problems are going to be calculator problems for us now. So this one is giving us the derivative of a function. It says f prime is 3 minus e to the sine 3x, and we want to know which of these things must be true on the interval 0 to 2 pi. So the first one is that f has 4 points of inflection. Well, points of inflection should always occur, right, when f double prime changes from positive to negative or vice versa, right? Well, that changes when f prime goes from increasing to decreasing. In other words, when f prime has a max or a min. So what we're going to want to do is we're going to want to graph this derivative and see how many maxima or minima it has on the interval from 0 to 2 pi. So we're going to open up our graphing calculator here. We're going to go into the y equals screen. We're going to graph our function 3 minus e to the sine of 3x. So second natural log gives you e to a power sine of 3x. And of course, you want to make sure you're in radians, which I know that I am. And when I graph it, I get this, which isn't real helpful because I haven't changed my window settings. So I want to change my window settings so that all I'm looking at is the section from 0 to 2 pi. So I hit window, and I change my x minimum to 0 and my x maximum to 2 pi. Right? And now when I hit graph, it's only going to show me the portion between 0 and 2 pi. So if we look at this, we can see that this has a minimum, then a maximum, then a minimum, then a maximum, then a minimum, then a maximum on that interval, which means we have 6 maxima or minima on this interval, which means that we have 6 points of inflection. So we certainly do not have 4 points of inflection, we have 6. So number 1, not true, which means we can eliminate A, C, and E. Now for number 2 here, it says f is increasing. Well, f is increasing if its derivative is positive. So if we look back at our graph on 0 to 2 pi, well, it sure looks like the values of this are always positive. Right? We might not be quite sure about if these little minima here, if it crosses through, but if we were to zoom in there, we would see that it is not crossing through the x-axis and having any negative values there. So we would know that this thing is always increasing, which means that 2 is true. So yes on this one, no on the first one, which means we didn't eliminate any of the answer choices there. In fact, we didn't even really need to check that because our only options left were 2 or 2 and 3. Then it says f has a local maximum at x equals pi over 2. Well, we just said that f is always increasing. So if we are always increasing, there is no way for us to have a local maximum. And a local maximum anyway would be when f prime goes from positive to negative, right? Because that's when the derivative is going from positive to negative, meaning the function goes from increasing to decreasing, giving us a max. Well, we just looked at it. That never happens, right? So we do not have a maximum at pi over 2. That's a no. So the answer is 2 only. All right, for our next one here, we have a particle moving along a line so that its velocity is given by v of t is equal to negative t cubed plus 2t squared plus 2 to the negative t for t greater than or equal to 0. We want to know when is the speed of the particle increasing. So we have to be careful here because speed is the absolute value of velocity. It's not asking when the velocity is increasing. It's asking when the speed is increasing. So since this is a calculator question, the easiest way to do this is to just graph the absolute value of the velocity in our graphing calculator, which is what we will do in just a second. Now, if this wasn't a calculator question, right, we know that speed is increasing if velocity and acceleration have the same sign. So if this was a non-calculator question, you would have to go through and see when the velocity is positive and negative, and see when the acceleration is positive and negative. But since it's a calculator question, we can just graph this using absolute value. So we're going to hit zoom first and go back to zoom standard, so we have our regular window here. And then we're going to go into our y equals, clear out that equation, and we're going to put in our new function, right? starting with absolute value, which is in the math window. So we're going to hit math. And you're going to go to the second column, and it's option number 1. So now we have our absolute value, and we have negative, and it's t cubed, but we'll use x because that's our option here. Negative x cubed plus 2x squared plus 2 to the power of negative x. And that's all inside of our absolute value. Now, when we graph this, we want to know when is this increasing, right? So it sure looks like, in fact, it doesn't really matter to the left of 0, but I'm going to change my window to 0 to 10. So really all I'm looking at is from 0 to 10. And so now I think the best thing for us to do here is to try and figure out if we have a minimum at anything between 0 and 1. So we'll hit second, trace, and we'll calculate the minimum. And we have to scroll over to the left here because my cursor starts at 5. But if I scroll over far enough, really close over here to 0, right, where it says left bound, I'm going to hit enter. Then I'm going to go to the right a little bit and hit enter on right bound and then have it guess. And it does tell me that there is a minimum there, 0.1767331, which means that this starts increasing at, rounded to 3 decimals, 0.177. So we're going to go over here and say from 0.177 to something, we're increasing. So now we'll go back to our graphing calculator. We'll do second, trace, and we'll find option 4, the maximum. We'll scroll over till we're pretty close to that maximum, hit enter, and then scroll over till we are past that maximum, hit enter, and hit enter again. And we can see that it's going to stop increasing at 1.256. So 1.256 is where we stop increasing. So that's one of our intervals, 0.177 to 1.256. So that eliminates A, B, and C. Just leaves us with D and E. And I think we can pretty much see that it's going to be option E, because if we look back at the graph, we can see that it starts increasing again around 2. Now, we'll just show that that is the value that was given to us. We're going to pick option 3. We'll calculate our minimum. We'll go over close to the minimum, hit enter. Scroll to the right of the minimum, hit enter once more, and see that it starts increasing again at 2.057. And so we'll say union 2.057, and it looked like it was increasing forever, which makes sense because as x goes towards infinity, that's going to just keep getting bigger and bigger. The absolute values of this thing are going to keep getting bigger and bigger, right? Because our velocity is going to keep getting to be a bigger and bigger negative. Okay, so our final answer here is choice E. All right, for our next one here, we're looking at line L. Line L is tangent to y equals e to the x at the point k, comma, e to the k. And we want to know the positive value of k when the y-intercept of L is 1/2. We have a lot going on here. But the first thing to recognize is that what we need is an equation for line L. Well, line L has the point k e to the k, right? And then we want to find the tangent line. Well, that means we need the derivative, which is e to the x. And it's tangent at the point when x is k. So y prime of k, or our slope, should just be e to the k. So we're looking at a line that has a slope of e to the k and contains the point k, comma, e to the k. So that'll be y minus e to the k equals our slope, e to the k, times x minus k. Well, we want to know for what value of k is the y-intercept 1/2. Well, the y-intercept is 1/2 at the point when x is 0 and y is 1/2. So we'll now go over here we'll plug in 1/2 for y. So we have 1/2 minus e to the k equals e to the k times 0 minus k, or negative k. So now we have a couple options as to how to solve this. I'm just going to leave it in this form. 1/2 minus e to the k is equal to negative k e to the k. And I'm just going to graph each of these two things on my graphing calculator, replacing the k's with x's. And then I'm going to look for their point of intersection. So I will go back to my graphing calculator. I'm going to hit zoom and option 6 to put my window back to its standard range. I'm going to hit y equals, clear out that equation, and I'm going to graph 1/2, or 0.5, minus e to the x instead of e to the k. And I'm going to graph in the second equation, negative x e to the x, right? Instead of negative k e to the k. And I will graph them there. And it looks like they intersect a couple of times. So if we read the question says, what is the positive value of k? So we want to make sure that we get the positive value of k. So we'll hit second. We'll hit trace. We want the intersection point of the two functions, so we'll choose intersect. We'll hit enter. We'll go till we're kind of close to that intersection point, but maybe to the left of it a bit. Hit enter. Then go kind of to the right of that intersection point, hit enter, and hit enter again, and see that that intersection point happens when the x value for these functions is 0.768039, or in other words, that'd be when the k value is 0.768. So we'd write k is equal to 0.768, and we'd look over here and see that that is option B. Okay, for our next one here, we are looking for when f has a relative maximum, and we're given a derivative, right? X cubed minus 4 sine of x squared plus 1. So we want to know when that has a maximum. So it has a maximum if f goes from increasing to decreasing, which means that f prime goes from positive to negative, which means all we really need to do is graph our derivative on our graphing calculator on the interval negative 2.5 to 2.5 and see when it goes from positive to negative. So we'll go back to our graphing calculator. We're already on the right zoom, so we'll just clear out from the y equals screen both of our equations. We'll type in our new equation, which is x to the third minus, what was it, minus 4 sine squared, or sine of x squared, so sine of x squared, and then plus 1. And we'll graph it, and we get this. We could probably just get our answer from here pretty easily enough, but just to make sure, I always like to change my window to the what's given in the problem. So I hit window, change the x min to negative 2.5, and the x max to positive 2.5. And when I graph this, I can see that there is very clearly only one place where the derivative, which is this function, goes from positive to negative, somewhere there between 0 and 1, right? It goes from negative to positive here, so we'd have a minimum, and negative to positive here, so we'd have a minimum. But we go from positive to negative here, which gives us a maximum. So we want to use second, trace, calculate option 2, which is 0, and we want to find the coordinates of that x-intercept. So we go pretty close to it on the left side and hit enter. We go a little past it on the right side and hit enter. We hit enter again, and we get 0.542. So the only place where that happens is at 0.542. All right, just 2 more problems to go here. So here we've got the volume of a sphere is decreasing at a constant rate of 3 cubic centimeters per second. So right off the bat, we can probably assume this is a related rate question, and we'll say dv dt equals -3, making sure we make it a negative because it's decreasing. And then it says at the instant when the radius of the sphere is decreasing at 0.25 centimeters per second. So that'd be a dr dt of negative 0.25, right, or negative 1/4. We want to know what the radius of the sphere is. So all we have to do is take the derivative of the volume formula for a sphere, which is dv dt, is 4/3 pi r cubed. So the derivative should be 4 pi r squared dr dt. We'll just plug in the values that we were given. Negative 3 equals 4 pi times the radius squared, which is what we're looking for, the radius, times negative 0.25. So, we just need to then solve this for r. We'll do a little bit of the work by hand, so we don't have to put as much into the calculator. A 4 and a 0.25 should cancel out. So, and then the negative and the negative should cancel out. So really what we've got here is r squared equals 3 over, not 3 over root pi, 3 over pi. And then we just want to find r, which should be the square root of 3 over pi. Now we could probably just take a pretty good guess that that's going to be 0.977 here, because 3 over pi is just barely less than 1. And if we square root something just barely less than 1, we should get something really close to 1. But we'll just confirm it here. We go back to our graphing calculator, right? If we do the square root of 3 over pi, we can see that we do get 0.97720500238, which rounds to 0.977. All right, and here is our last one, not a multiple choice question here. We've got a question that says, use the intermediate value theorem to show that e to the x plus x equals 0 has a solution, and then use Newton's method to find the solution, accurate to 9 decimals. So what we would first need to do is we would need to state, if we're using the intermediate value theorem, that f of x, which is e to the x plus x, is continuous, right? It's continuous for all real numbers, right? So because it is a sum of known continuous functions, right? E to the x we know is continuous for all real numbers, and x is continuous for all real numbers. Therefore, the sum of them is continuous for all real numbers as well. Then we need to find a place where it's going to change signs. Well, a good place to start is just looking at what f of 0 is. F of 0 is e to the 0 plus 0, which is just 1. And then we need to think about what's going to happen if I go to the right or to the left of 0. If I go to the right of 0, those numbers are just going to keep getting bigger, right? So I want to go to the left. Let's see what I get if I plug in negative 1. Well, I get e to the negative 1 minus 1, which would be 1 over e minus 1. Well, 1 over e is less than 1, right? Because e is 2.7128 something, something, something. So that's a fraction that's less than 1. Minus 1 is less than 0. So between negative 1 and 0, this function changes signs. And we know it's continuous on negative 1 to 0 because it was continuous for all real numbers. So we might want to clarify over here, e to the x plus x is continuous for all real because it's a sum of continuous functions. So it must be continuous on the interval from negative 1 to 0, right? So it's continuous on negative 1 to 0 as well. And so now we know that the function's continuous, and we know that it changes signs between negative 1 and 0. So we can use Newton's method to approximate the solution of it, starting with perhaps a first guess of negative 1/2, because that's directly between negative 1 and 0. So we'll start out here with x sub n plus 1 is equal to x sub n minus, and then this fraction that we have for Newton's method, right? And that was f of x sub n here in the numerator, and it's f prime of x sub n in the denominator. That was Newton's method, the formula for it. So if f of x was e to the x plus x, then f prime of x should just be e to the x plus 1. So we end up with x sub n minus e to the x sub n plus x sub n. over e to the x sub n plus 1. So when we go to our graphing calculator to do this, we want to start by typing in negative 0.5 and hitting enter. And then we just type in the same formula we had, but anywhere we had x sub n, we're going to replace it with second and the negative sign, which puts in the previous answer. So we have x sub n minus, and if your calculator does the nice fraction with alpha and then x, do that. If it doesn't, make sure you put the whole fraction in parentheses and the whole numerator in parentheses and the whole denominator in parentheses. So you need 3 sets of parentheses. So now we'll have e to the x sub n, and then it was plus x sub n over e to the x sub n plus 1. And we hit enter. It gives us our first value here. So we'll write this down. X sub 1 is equal to negative 0.56631110032. And then we'll hit enter again. It'll give us our second value. Okay. So we'll put that one in. X is equal to negative 0.567143165. Then we'll hit enter again, and we'll get this value. So we'll put that one in. X sub 3 is equal to negative 0.5671432,904. And when we hit enter again, we can see we get the exact same values, which means that x sub 4 was the same, which means that to at least 9 decimals, that actually looks like that's 10 decimals, accurate to 10 decimals, the solution to e to the x plus x equals 0 is negative 0.5671432,904. And that is the end of our walkthrough for that first semester 1 review homework assignment. And again, remember that this is not covering every single thing from the entire semester. It's not a comprehensive review for the midterm. You need to do all the other reviews as well. This is just some problems that will be useful to you for the midterm. But that is it for now.